what it's all about, right? We observe on the sky galaxies, and basically we're looking for patterns in the shapes and the orientations of these galaxies. But as is indicated here, well, the CMB could get lensed, but these different paths sort of depend on whether these galaxies are close to other galaxies. So it's not just, and we'll hear more about it tomorrow, just gravitational lensing when we see this, because some of these galaxies might be physically associated and therefore intrinsically aligned. And we need to decouple that from correlations of galaxies that are in the background and are actually gravitationally lensed. But both are gravitational effects. They lead to very similar results. And so that's what it's trying to indicate it here. There's shapes and distances. And so this is really what all these modern surveys try to do, is really to slice the universe. And for that, we need, as I said, both shapes. That's been in the lensing field mostly where the emphasis is on. But we also need distances. And that's really, I think, one of the key areas where also different surveys distinguish themselves, because I think this plot has also been shown, but I think it's still good to reflect on this. It's sort of summarizing the various surveys, so the surveys that are finishing right now, and we're moving up in the number of objects, right? We're now, right, Euclid will reach 1.5 billion LSST, similar numbers. And so there's sort of two axes here. There's the area and the number density, so that allows you to sort of probe different regimes, different redshift ranges. But I think what is also good here is that it's trying to indicate sort of by the spectrum, the wavelength coverage of these surveys. And if you look at the stage 3 surveys, this is where KITS, which I'll briefly talk about, distinguish itself from, say, HSC or DES. So you can see they probe different regions in this parameter space. And the same is true, although they appear a bit closer here, but Roman sort of fits its own spot in this parameter space. And I think this is really important. So for stage 3, this has proven to be very useful, because these different choices sort of highlight arguably different things that could go wrong, so different systematics. So, and that's good to start off with, although I think in the end we find that everybody is sort of finding consistent results. So these different systematics are also under control. But yeah, the measurements we're trying to do are hard. And so basically having 3 identical experiments wouldn't teach us much. So it's actually good that there's this diversity in depth, in wavelength coverage, and number density to explore, and not only focusing on the systematics, but also the redshift range that can be covered. So there's also complementarity, both in terms of testing things, but also in terms of science application. And so, right, I think given the challenge of measuring these cosmological lensing signals, it's quite remarkable when we compare different measurements, different surveys, the different stage 3 surveys, how good the agreement is. And the way we measure this is what current measurements measure really, really well, is what we call the clumpiness of the universe, a combination of sigma 8 and omega matter. So it's really the amount of variance in the matter density field. And this is what is measured to first order. So that's the nice thing to do. And here you see DESI year 3, and then also KITS and HSC here in blue. And they agree quite well amongst themselves. They agree somewhat less well with the Planck results. So this is this S8 tension that has been mentioned earlier. But I think apart from whether or not there is a tension, right, I think the important thing is these early surveys already are competitive with the CMB when it comes to this parameter. Now, you could argue, who cares about S8? Well, that's a good question to ask, but I think it's an important test of the field, because remember, for the young people here, where we came from, right? 25 years ago, people would not have believed this plot could exist. Right? I think that is important to keep in mind. And we're trying to, of course, push an order of magnitude more in the coming decade. I think what is very good in the lensing community is that there's good communication between the different teams. And so I think one thing that has been very, very useful is a very detailed comparison between DES and KITS, because you literally make well, maybe not 1,000 choices, but we make many, many choices about where to cut scales, how to calibrate redshift, how to calibrate shapes, how to deal with intrinsic alignment, how to deal with baryon physics. So there's a lot of choices that are made, and these different surveys, on one hand, it's good to have these different analysis teams. Well, they make different choices. And I don't think there's a good and right choice, right? There's also the space of choices themselves also lead to a coherent result. But you can play with all kinds of choices, and what you see that overall these results are actually quite robust. But still, it was a very useful exercise because it highlighted what the different choices do to the different surveys also. And so I think that is something really to keep in mind as we move on forward, because there's a lot to be learned from talking to the other teams. But overall, I think, well, yeah, the choice of the analysis matter, but only somewhat. And well, I've been known to joke about why, if you want to do cosmology, you better do something complicated, because with all these choices, the central value theorem makes sure that you end up with the right answer. So I was somewhat surprised that when we unblinded the kids' final analysis, that actually something did change. So this is the latest result from kids, and I think it's important to mention because I've heard several talks about an SA tension, and I'm not sure, well, I'm not even sure it was ever there, but it was useful to motivate the field. But actually the latest kids result are in very good agreement with the Planck analysis. And so it's really a series of improvements on many, many fronts. But two important drivers for the change is more data. So more data always helps. So really, even though it looks like it's a relatively modest increase in area, by adding more high redshift galaxies, the effective constraining power was constrained quite a bit. And one is more related to systematic, in particular calibration of the photometric redshift. So there's a big improvement in the redshift calibration, which not only help to include these higher redshift galaxies, but also improve things for the other redshifts. And so I think, right, so whether or not this is the right answer, we'll find out when we get better data. But one thing that is sort of suggestive that internally consistency check, this is the most internally consistent analysis of the kids' data so far. So that should count for something. Like compared to when we leave out data, when we do various tests, the results are internally very consistent. And that wasn't quite the case with previous analysis. So we've done, again, all these kinds of tests. But I think the upshot is that there's now very good agreement. And so I think in general, one should be careful with 2 sigma results. Right? They're, right, as the PI of kids like to say, it's good enough to motivate them to get up in the morning and analyze the data, but not bad enough to keep them awake at night, right? So, and I think that's the situation you want to be in. But ultimately, of course, why we're here is because we want better data. We want a lot more data, but also better data. And nothing better than real data. So here's a deep Subaru image, which is a good proxy for LSST year 10. And this is the same area with Hubble, which is a good proxy for Euclid or Rubin, right? And when it comes to lensing measurements, like I prefer this one, but that doesn't say you can still use this, of course, as well. But this is the reason why we have space-based lensing surveys, because having such sharp imaging should help a lot. But of course, when I started my PhD, we had Hubble, and the first thing we did is we want to look at clusters, and we had to mosaic clusters, right? We did, my first paper was CL 1358. I think that was the largest field of HST. I think that was like, must be 16 or 25 pointings with WIFPIC 2, right? So that probably for the people that dates me. But that's the amazing thing. Now we're entering a time where those kind of observations you do in one shot, right? So these are already upgrades from WIFPIC 2. These are the HST and James Webb cameras put into context in Roman, and also the Euclid one. So I think it's also good to remind people the Euclid field of view is twice that of Roman, right? So, but both are enormous steps up from what is currently in space or prior to Euclid. Right, so this is really changing what we can do, because there's lots of objects in the sky that are a lot bigger than this, right? And that is really enabling all this new science. So just quickly, there's been a few talks that mentioned Euclid already. It's designed to do weak gravitational lensing and the clustering of galaxies. And so in many regards, it shares similarities with Roman, but Ismail Terrain also showed, right, there's differences, right? Roman goes quite a bit deeper, especially in the infrared compared to Euclid. So, but Euclid will do more area, 14,000 square degrees, but we'll also get lots and lots of redshifts that complement these measurements. Now, I could not resist to show real pictures. I hope you've all seen them already, but in case you haven't, right, go online and look at these images, because the only way to really look at them is at full resolution, right? Each image of Euclid is 20,000 by 20,000 pixels. There's actually no projector in the world that can actually show them, so you have to zoom in and stuff. But these are some of the early release observations, and that is really what is remarkable about these data. You can actually waste a lot of time looking at these, and I think, I'm not sure if Joe is still here, but this is prettier than the CMB, I would say. Right, but you have here a Perseus cluster, which really, you can see all the detailed globular clusters, so that the science is rich. So these early release observations, I think, were a really good idea, and it's also nice to see Roman is thinking something the same, where you can use science and PR at the same time, because these data, even if you do them for PR, they're scientifically so powerful, right, that you can do quite remarkable stuff. But what is really remarkable is that as you zoom in, right now you see something the size of a Hubble image, and you see all the detail, right? And that's what I want to measure shapes. Just if you want to play with it, the first data are public. So in March, we released the first 0.4% of the data. Here I'm only showing 0.14% of that. But that's especially not so much for cosmology, but for people studying galaxy evolution, right? That is like Cosmos, but 50 square degrees, so way, way bigger than the first fields. And I've picked here already a gravitational lens image, because that is really one of the areas. There's many areas, just like what we see the wide range of science that Roman will do. Euclid is already starting to transform certain areas, low surface brightness studies, but also strong gravitational lenses. In this small area we looked at, we already doubled the number of known strong gravitational lenses. And actually literally one of the very first images, not even in focus, people discovered a little Einstein ring here in a galaxy. It's an NGC galaxy, so people knew about it for over 100 years. And that shows the discovery potential of these things. You just look at a random image and you will see something people haven't seen before. And so really we're changing the way people study gravitational lenses. This one was still spatial, so people spent a lot of time writing a paper on this. But I'm not sure the journal will be happy if we submit 100,000 papers for every single. They're already complaining we're doing too much science with Euclid, right? But we have to start with moving to statistical analysis of strong gravitational lenses. So I think it's super exciting. But let's look ahead a little bit, because right, what is clear, and I think is still remarkable, even though we're running out of universe, right, from when I was finishing my PhD to where we are in the future, right, this is a log linear plot, purely signal to noise, but that's an exponential increase in the amount of data we're using for cosmology. We're really in a quite remarkable time. Unfortunately, you can't continue this because there's no more universe. But of course, there's still a little bit of depth. So this is where Roman, for instance, helps a lot. But I think the important thing is that this is more precision, right? But there was a reason why people were worried 25 years ago about lensing, because it's not just about precision. There's a lot of potential information we're getting, right? But you try to do cosmology. Is it a Gaussian likelihood? Maybe not, probably okay assumption. But so this is, of course, what we focus on, right? We've launched or going to launch telescopes to give us good data vectors and positions, shapes, redshifts, PSF errors. I won't bore you with that. But then there's on the theory side, it's like, how do you correlate these measurements? So do we need to compress the data to make the covariance more handled? Because otherwise you get very large calculations that need to be done, covariances that are hard to compute. But it's, of course, the more interesting, the theory vectors, the cosmology, maybe some new physics, who knows? But there's also the stuff that we as cosmologists don't like, baryon physics, intrinsic alignments, right? So there's the stuff that prevents us from finding the new physics. And that is really, I think, where a lot of progress is needed, because as we'll see at the end, I'm concerned we won't be able to analyze, well, we will be able to analyze the data, but not to the fullest of that potential information that is there. Because one thing that is very clear is we need to combine probes. So even when we think of Euclid as weak lensing, and I know it's been confusing for many people, we always meant sort of weak lensing with the position, so photometric clustering and the cross correlation of galaxy-galaxy lensing, because only then can we really reach percent or sub-percent precision or dark matter, a dark energy equation of state parameters. Right, so that's always been the plan, is to cross-correlate. But then that leads to the question, okay, that's all nice, but really what you then need to solve is to how galaxies populate the dark matter halos. Right, so it links this sort of apparently clean measurement to something messy like galaxy formation. But it's very clear, so we've done this analysis, right? You can say, okay, what kind of scales would you stop using the data? Because of course the data measures things to all scales. And it's clear that on small scales you can get a lot of improvement. And what is important is that the physics on these different scales is important. And here you see two simulations with and without feedback. But I think what is very important is that it's correlated. On small scales, you get astrophysics. On large scale, you have cosmology. But those are not independent things, right? This is not a data science problem. It's a physics problem. And a lot of analysis now, they sort of like, oh, I like to play safe. And I'm from the Netherlands, so I'm quite familiar with this. But really, I prefer the mountains. And not because it's more dangerous, but it's more interesting. So we should not be afraid to push into an area where we don't know things that well, because it's also an opportunity, right? Because that's what I'm trying to emphasize. These scales are linked by physics. These are not, it's not that what happens on very small scales is independent what happens on large scales. The challenge is, of course, linking them together in a way that is consistent with all the data we have. But I think this is what is important. So it's very nice to see yesterday people thinking in terms of, in simulations, getting better prescriptions of the data, so this multi-dent data. But I think what is also important to remember is that these very surveys that we're using for cosmology give us information about the mass scales. They allow us to make that link between mass and galaxies. And so we can, for instance, look at the effects of feedback. We can combine with a Z or X-ray measurements and predict what we should see. And of course, simulations play a very important role there because they can help us inform also these observations. And for instance, when something people are very worried about is feedback, but if you look in simulations, it turns out this feedback is a single parameter. And I think that's with a lot of these things we're worried about with all these nuisance parameters, apart from baryon physics, it's mostly just gravity. There's zero numbers except for the cosmological parameters. So we're doing something wrong as we're adding more nuisance parameters because nature tells us it should be possible with far fewer parameters. Now, it doesn't tell us how to solve it, but something which I think is quite useful, there's actually an old idea going back to Dragan Hutterer, but even before that, is that we're combining with higher order statistics because the phases do matter and people are starting to explore this. It's either through clusters, but you can also do this directly because these higher order correlations to get consistency, and this is an old result with Elisabetta Semboloni, that actually once you combine more information, and of course that's what some of these forward modeling approaches also trying to do, but just doing 2 and 3 points already, if you want a consistent cosmology, forces you to constrain additional baryonic parameters. So a lot of these issues also by combining data cleverly, instead of taking this staying in the field of grass, we can learn a lot more. So I think that what is really important is that we take a more holistic approach. Don't forget that we're physicists and not data scientists, right? So this is really important. There's links there, and maybe you don't want to learn about galaxy formation, but I think it's worth trying to learn a little more and connect this all together. Just to conclude, so I think we're really in a very, very great time to learn more about dark matter, dark energy, but really we can learn a lot about the universe and much, much more if we really start focusing on these small scales and try to push there, and in particular use these very surveys and start thinking of how we can use Roman, Euclid, and LSST to probe those small scales and sort of link everything together. Thank you.
Questions. We probably have time for 1 or 2 quick questions. And also just to mention, people online are also welcome to ask questions. Feel free to write in the chat.
I thought that would be controversial enough. But
Hey, if we ask the galaxy formation experts, can we model feedback with one parameter? They think we're joking. So do you worry that we're going, by being too aggressive with our modeling choices, or by taking a relation that is entirely from simulation, from data, that we might bias out of knowledge?
Sure, but I think at the same time, on the scales we're looking, it's still gravity, right? So gas you give some kinetic energy to gas particles, but what on the scales we're probing, and I'm not saying we should go down to 100 kiloparsec, but once you go to megaparsec, it's just gravity. But this is what you're seeing in the simulations. This is why it's a 1-parameter family. I think, okay, that may be too simplistic, but it does show that, especially, you've been doing like KSZ. So when we take a multi-wavelength approach, maybe add X-rays, but sort of try to understand what happens on these very small scales, it does have implication. It does restrict the freedom. And of course, we will need nuisance parameters, but so then the proper Bayesian way, we will actually put informative priors on it. So we have to find the right balance. But now I sometimes feel people are too conservative because I'm not gonna touch this. And so I'm just gonna cut out all scales where I have some sensitivity to something I think is actually interesting to study.
All right, yeah, maybe one more question from
It's not a question, just a comment. So I think on the plot you showed of Euclid forecast, we should probably add that galaxy clustering from the Galaxy Redshift survey on Euclid is one of the 2 primary probes of dark energy on Euclid. Weaklings is only one.
Yeah, no, that's what I had both.
No one's thinking that Euclid is only weaklings only, so no worries.
No, but the weak lensing probe has the photometric clustering and cross correlation.
It's the spectroscopic.
Yeah, that's in addition, yeah.
Yeah, it's an independent survey, but highly complementary.
Yeah.
All right, any questions? Okay.
Oh, yes.
Oh, okay. There's
A question online?
What would be your ideal Roman survey?
Well, I think it's sort of, right, given we have Euclid already, I think the current survey is, well, I'm not sure it's completely optimized, but the added depth, I think, is very important because it adds a different dimension. So I don't think Roman doing the same 14,000 square degree would have been useful, right? So I think it fits very nicely in this space of surveys that we have because LST just started. Yeah, whether it's optimal, but I would guess it's close to optimal.
all right. One last question.
If you could go back in time and redesign the disk band 550 to 900 nanometers.
Yeah, I would pick it shorter. Yeah, because we were obsessed with getting photons. Actually, what is more important is actually because we have this sharp cutoff, which then leads to out-of-band leakage, and having a slightly curved one would have avoided that. So yeah.
All right. Let's thank Hank again.
Let's see, right?
So next we have Tansu Delan, who will tell us about the Roman view of strong gravitational lenses.
Thank you. Hello, everyone. I'm Tansu Delan, assistant professor at Washington University, and today I'll be talking about strong lenses in the context of Roman. I guess we've had multiple talks on weak lensing. This will be a shift of gear. Magnifications will go infinite. It will get interesting. So it will be half a status report on our wide field science program. And in the first half, actually, I'll just use my time to motivate the science case, I guess, in the broader context of other cosmological probes that Roman will enable. So as I mentioned, this research has been funded by the Roman Wide Field Science Program, as well as seed funding from our McDonald Center for Space Sciences at WashU. All right, so let's get started with a reminder. So the dark matter problem, basically, especially the esoteric nature of its particle nature, continues to employ all of us, and it remains one of our, I guess, outstanding problems in cosmology, in addition to dark energy. And there are multiple, well, I guess, a zoo of ways of trying to search for dark matter. Two that are closest to my heart are over there. On the left, for example, you see a gamma ray signature that could come from annihilation. On the right, you see basically what we refer to as gravitational imaging based on strong lenses, which I will now describe. This is part of indirect detection of dark matter. So to set the stage, we start the universe basically by having these very small mass halos that collapse first with very high concentrations, very low virial radii, and then they start to get accreted into larger and more massive halos over time. So this is basically a hierarchical process. In this lambda cold dark matter paradigm, we end up with halos that look like this at the current time, where major halos, more massive ones, essentially have substructure locked up in them. Obviously, all of these subhalos are subject to evaporation. The escape velocity is finite, so over time, some of dark matter particles escape, and others get tidally stretched and then dissipate. So the picture on the right essentially is how they look. And not all of these actually contain or otherwise form stars. There's quenching of star formation due to the reionization, where these very low mass halos do not have enough virial temperature to actually form stars, cool and form stars. So on the left is an archaic plot, but still kind of holds. So if you basically extrapolate what we actually see, well, about maybe 1 kilometer per second velocity dispersion, if you assume, you should basically get over 500, probably 1,000 or so Milky Way halo dwarf galaxies. There is this whole industry on that problem, which I won't really go into, whether there is a missing satellites problem or not. it's because when we discuss that problem, we rely on those galaxies being detectable with light. And that is actually not a given thing. So basically, in this science case, we don't care about that because we work with gravity. Because in strong lenses, what we care about is the total mass and its distribution on the lens plane. And the light distribution on the source plane basically gets remapped, which we then basically can model using the so-called lens equation, where alpha is the deflection, which itself depends on theta, the lens plane coordinates. And here is just a visualization of this that we recently made for an outreach event at WashU. So you can see that these point sources, or I guess here is a galaxy, can form rings or otherwise multiple images. And this is the first discovery of a strong lens, a doubly imaged quasar. By the way, we don't use quasars because quasars are point sources. They're about nanoarc-second wide, and they're too small, which means that a single star in the lensing galaxy can microlens, which then introduces flux anomalies, which is really hard to model. So we disregard them. In this science case, we focus on galaxy-galaxy type lenses because of this reason. So I won't really go into the details of how this is done. Unfortunately, I don't have time. We basically model it and then look at the residual and try to interpret the residual with the understanding of trying to remove, for example, the microlensing hypothesis away, as well as long as you remain either in IR, infrared, or radio, there's also no dust absorption. In optical, there is also the possibility of dust absorption, so it gets complicated. This is just the very short history of this problem. Kind of started early 2000s. We had the SLACS, which is basically the largest data set we have. And then this is from 2012. It's a Nature paper by Simona and her team. And I don't have time to go into detail about that. I'll just highlight one thing. You need diffraction limited imaging in order to be sensitive to low mass halos. This is basically what I want you to remember. And this slide is basically how I started working on this during my PhD. I worked on a methodology to do this in a paradigm I refer to as transdimensional gravitational imaging, in the sense that the catalog we fit is actually transdimensional. You can merge, split, kill, add subhalos to actually solve the same problem. Now, moving forward, I took a break from cosmology for a few years during postdoc, but when I started faculty position, I started focusing on this problem again. And by that time, W first became Roman, and we actually had a rough timeline for when things would happen. So I responded along with my colleague Simon to the white paper process. Quick reminder, this is basically how the situation looks even with the nominal wide area survey. So the reference mission that we had even before the ROTAC process, if you just do the basic calculation of how many strong lenses you'll get, how much time you'll be spending staring at them, the amount of data we will gather on these strong lenses is about an order of magnitude higher than the total amount of data we had from Hubble Space Telescope on these strong lenses. The wide field instrument will enable that, the wide area, the field of view, it's about 100 to 200 times that of Hubble. And here, basically, it's a comparison of how strong lenses look differently in Roman, Euclid, LSST, and HST. So the white paper basically made a recommendation that we have a deep tier of high latitude wide area survey, and the recent ROTAC process basically introduced this deep high latitude wide area survey, the 20 squared arc second addition to it, which I guess falls just below our recommendation, but still is very useful. So that 20 squared arc seconds will give us about 100 more detections, and we expect roughly the same amount from the time domain survey as well. So we will have hundreds, maybe up to about 1,000 so-called grade A strong lenses. And grade A in this context means high signal to noise, to be particular about 200, given some definition of signal to noise, obviously. So This is basically about our wide field science program. The team is pretty small compared to PITS, I guess. We are based at 2 different universities, Washington University, Bryce and I assume my graduate students, and Jody, my undergrad, as well as Simon, my co-I, and his students, Alan, Shiwan, and Rahul. And we also have a list of collaborators that we worked on for our first paper that recently came out, which is here. So if I don't have time to go into all the details, but please check out our data set, which is now on Zenodo, as well as our pipeline called Megiro, which is basically which is this end-to-end pipeline to simulate and eventually discover and characterize strong lenses with Roman. It interfaces various other packages, which again, I won't have time to go into, but please do check these out. The paper was recently published in AppJ. So a couple of plots from the paper. This is how the wide field instrument will look. This is from STIPS software, but these individual panels, this is a strong lens, and it's in SCA4, Silicon Chip Assembly 4, and the other panels are essentially residuals for the same system. So how kind of your PSF varies, which you can also see here. Roman is 6 struts, so you can actually see that in the PSF, and here are the residuals of that across the wide field instrument focal plane. So the color scheme here is essentially the quadrature sum of the Zernike coefficients, which we took into account using cycle 9 data and propagated all of that, the detector systematics, as well as the optical aberrations. The detector systematics are shown here. For example, you see interpixel capacitance, you see nonlinearity here, and reciprocity failure. I believe this is dark current. So we included all of these effects. And then we calculated SNRs over our field of view. So we then asked the question of what basically is the mass of the halo that we can detect at a given point. And as a reminder, in case you don't think about this problem all the time, in order for you to be sensitive to a given subhalo, that subhalo needs to be in the vicinity of a multiple image. There may be 1, 3, 5, etc. Some of them, though, usually one of the images is demagnified, so we typically get 1, 2, 4, 6 images. But if your subhalo is far away from multiple images, you will not be sensitive to it, which is also the reason why we would want to avoid quasars, because quasars are point-like. So we want to, so to speak, have the largest real estate or largest solid angle on the lens plane in order to play this game. So this is our yield estimation. Too much to really go through, but a couple of takeaways. We will go much higher redshift than what's been possible before, which, by the way, means SLACS, the legacy survey, Bell's gallery combined. Certainly the sheer number will be much higher. To quote some numbers, 160,000 we predict over the entire high latitude wide area survey, and about 500 of them will be higher than signal to noise of 200, which means amenable to characterization of subhalos in this context. Okay, I don't have much time. So we also looked into the SCA-dependent systematics. We studied the minimum mass that we can go down to, which is modest at this point because we did not include dithering in this paper, which is a work in progress. We have another paper, so to speak, Megiro version 2, that's ongoing where we will do that. And yeah, I realize I've run out of time, so I will skip these. There is documentation on Megiro, so if you're interested, if you want to use strong lensing in your science, go check that out. There's documentation, and this is about the press release that went out regarding Roman based on our paper that was then picked up by several channels. This was last month, and my final slide, so this is about the Roman Data Challenge that we are now organizing as part of the promised wide field science program activities. So we are about to start this. You will hear about this through various channels starting this fall. We have the data product already ready. We are now working on the peripheral organization to put this on the Roman research nexus, and you will go ahead, for those of you who want to work with strong lensing data, you will be able to go form teams on the Roman nexus and then start playing around with this data that has all the systematics that you could imagine regarding strong lenses. So I will just leave this slide up and take any questions.
Do you have an estimation how many like galaxy versus galaxy quasar?
Yeah. Right. We are actually in the process of doing this. The current paper is almost laser focused on our science case, for which we did not need quasars, but we are in the process of having a much more realistic and broader data set, which is actually being prepared. It has not been announced. It will go out before the second paper comes out. So definitely check out very soon. It will be ready.
Oh, one more. Andrew, yeah.
For your mock data challenge, what are the lens mass distributions? Where do they come from?
So the macro lens typically is drawn from a relation that is tied to SkyPi. So from SkyPi, we get the brightnesses, and then we use a scaling relation to essentially a mass to light ratio model to revert back to the virial mass. So we then draw subhalos consistent with that macro lens model using pi halo.
The macro lens model is like something parametric, or?
Yeah, it is parametric. Yes. Yes.
All right, we'll have to move on. You can maybe talk to Tansu later.
Okay.
But yeah, let's thank him.
Thanks.
So next we have Jiachuan Xu, who's going to tell us about kind of a different kind of lensing. So go ahead.
Thank you, Amy. It's my great honor to talk about pilot kinematic lensing measurements from DESI data here. This work is under the collaboration of kinematic lensing with the Hubble Space Telescope wide field science team. And this is our logo and also the Arizona Cosmology Lab. First, I'd like to say thank you to this whole brilliant collaboration team at University of Arizona and also at JPL. So first of all, let's go back to weak lensing measurements. If I want to summarize the weak lensing measurements in one sentence, that might be this equation. What we can measure is the ellipse of observed galaxies, and that's the only thing we can measure. It equals to the foreground cosmic shear plus the intrinsic shape of a galaxy. Unfortunately, this intrinsic shape, we cannot directly observe that. And those cosmic shear and intrinsic shape are degenerate together. And this we can assume that the intrinsic shape is like randomly distributed, but it's not. But this will introduce a shape noise that is on the order of 0.3 per galaxies. And typical shear for weak lensing is on the order of 0.01. That means for each single galaxies, we have an SRR measurements on person level for each single galaxies. If we want to do serious weak lensing analysis, then we have to include many faint galaxies. And the systematics of weak lensing are more challenging for those faint galaxies. For example, here's the flow chart of general weak lensing cosmology pipeline from, we have 2 pixels, we have 2 galaxies being shared, observed by telescope, to catalog, 2-point functions, and in the end to posterior inference. During each single step, there are many systematics that can include in this whole framework. And in a nutshell, weak lensing is very challenging to measure and model. However, when we further include the galaxy's kinematic informations, we can measure it by spectrum. The shape and shear degeneracies can be broken. And here, let me just show this simple cartoon again, and also remind you from yesterday's issues talk. So we have 2 galaxies. The first one is being sheared, but it's actually a face-on galaxy. The second one is not being sheared, it's just an inclined low redshift galaxies. If we put a grism on top of those 2 galaxies, the first one we would
see no rotation feature from the prism for the emission line. Is still elliptical. But for the second one, we can see rotation feature from the prism emission line spectra. By this way, we can break the degeneracies. So we know that the cosmic shear has two separate components. So here we have a detailed look at how each component impacts the data. On the right-hand side, I show the true shape of galaxies in the dashed contour and also the velocity field in the dashed contour. So the G-cross component would distort the galaxy along the diagonal directions, and we see the shape is slightly rotated and also distorted. The velocity field is also distorted, but we see that the axis symmetry of the outside rotation field is broken. So by this way, we can know like how large is G cross. For the G plus component is distorting along the x and y axis. We see the ellipticity and also the velocities are slightly distorted. The overall impact is similar to a change in the inclination angle of the galaxy. And we need more information to break these degeneracies. And that's coming from the Tolley-Fisher relations, where we can estimate the circular velocity from their broadband magnitude or stellar mass. And then we can guess how much is the inclination angle, then is how much is G plus. So we have built a forward modeling Bayesian inference pipeline to measure this kinetic lensing for each single galaxies. We have a galaxy SED model. We have a galaxy rotation kinematics model. We also have a galaxy morphology model, and then we apply shear to all of them to build a mock observation to map out the distribution of photons on RA, DAC, and also wavelengths. And then we build mock image and spectra and compare to the true observed image and spectra. And then we infer the posterior on not only G1, G2, but also position angle, inclination, and circular velocity, along with a long list of parameters for each single galaxy. The spectra can come from fiber measurements, slit, IFU, and for this conference interest, space-based prism. So Roman going to launch next year, but before we have fantastic data for validating the kinematic lensing methodology from JWST. So here I compare the instrument specs between JWST NIRCam prism and also the Roman wide field instrument prism. So we can see that JWST has roughly 3 times higher spectral resolution for the NIRCam prism than Roman. The wavelength is much wider, has much more than twice better spatial resolution than Roman. PSF size is similar, so JWST data is an excellent test bed for kinematic lensing and prepare us for a much larger area Roman kinematic lensing survey application. So the particular data set we are looking at now is the imaging from JACE data and this prism spectra from Fresco and also Congress. Here's a footprint showing the footprint of JACE in those red color and also the orange color patches. And this is the Goose North field and the Goose South field. Those are both well-studied field. And the Fresco prism coverage is shown in this rectangle, which is 62 Archimedes square per field. So that's not a very large field. But we do find many low redshift emission line galaxies. For example, for the Goose South field, we found roughly 180 Persian alpha emitters between redshift 1 and 2, and 31 Persian beta emitters from redshift 2 to 3, and some lower redshift bracket emission line. For some example of those galaxies, this is an example of Persian alpha emitters at redshift 1.6. You can see the RGB image from JACE and the direct image. And if you look at the prism, the dispersion direction is along the positive x. You can see clear distortion feature by comparing the prism and the image. And there are some other examples, the Persian beta emitters from redshift 2.1 and bracket beta emitters at even lower redshift. And you can see those next examples. Okay, before going to real data inference, we first look at mock JWST data analysis. So here we assume we have one broadband image from JWST F444W and one GRISM from the same band. The dispersion directions is along the X. The image is also, the measure axis is along the X axis. And we run our pipeline on this mock data. The posterior on G1 and G2 is here, but don't be fooled by the tiny posterior. The takeaway is the G1 is significantly biased if you compare the posterior and the vertical fiducial value. But G2 is kind of okay, is unbiased and have a tight error bar. The intuition is if we dispersed along the x-axis, we are measuring the velocity along the minor axis, which proportional to the rotation velocity times those factors and also the G2 component. So we can get one component relatively well measured by one spectra. And if we put another GRISM along the y-axis, we see the posterior is broadened a lot, but is kind of not biased in G1 and G2. This one is measuring the major axis velocity, which is roughly v circular times the inclination angle. If we combine the two dispersion spectra together, we arrive at the purple one, which gets unbiased and very nice tight measurement on the G1 and G2. And I also want to mention that the shear uncertainty of kinematic lensing depends on the inclination angle of the galaxy. So here is x-axis is the sign of the inclination angle. 0 means face on, 1 means edge on. And here is the bias of G1, G2 measurement, and here is the shift noise. And for a very wide range of inclination is way more below the 0.3 typical weak lensing shift noise, and can get very nice measurements from the mock analysis. But for high inclination angle, the posterior region is biased a lot. You can see the maximum posterior is okay, but the 1D mean is biased a lot. Now we are measuring this on real data. We see many subtle features from real data from JWST, thanks to the excellent instrument and data quality. So for example, here is an example JWST data. It's the original NIRCam image. If we take the asymmetric part of this image, we can see the residual, like other than the smooth exponential component. So we can see the red part and also the blue part are basically two spiral arms sparing out of the galaxies. We are starting to worry that the data quality is too high, that so far cannot model accurately, but we are working diligently on that. JWST is not pretty good at resolving the line of sight kinematics, but we have other graduate students at University of Arizona working on the substructures in the rotation velocities using manga FU data. So here's an snapshot of the typical velocity structure you might see. And so looking into the future, kinematic lensing can do beyond two-point statistics. And also JWST is not only providing testing data for Rubin itself is fantastic, and you can do fantastic stuff out of JWST and kinematic lensing. For example, we are considering about the weak lensing mass reconstructions from JWST with GRISM and image data. So we are looking at the Cosmos 3D dataset, which is 1/3 square degree NIRCam GRISM covered with the imaging part from the Cosmos Web data. And the left panel shows an illustrative figure of the HST era weak lensing. So the pixel size is chosen such that each pixel has a fixed SNR across different panels. And for HST era, we typically see a resolution of 1.5 arc-minute per pixel. But going to JWST, because we go much deeper, is 0.8 arc-minute. And with JWST kinematic lensing, we might go to 0.4, and combine weak lensing and kinematic lensing together, we might to enter into like 1/3 arc-minute per pixel. That's all. That's my conclusion now. Thank you.
And yeah, another reminder that people online can type their questions in the chat. Yeah. Hank.
So in the last figure, were you showing that you can apply kinematic lenses to every source? Because, or so it's not completely clear, but it looks like you get spatial improvement uniformly.
Yeah, that's assume we can select a realistic DESI galaxy sample from example JDESI deep field for these galaxies. We can do this kind of measurement, and they have order of magnitude better shape noise. Then we add the weak lensing and kinetic lensing sample together. Like back of envelope calculation, the improvement would be on the order of like this.
All right, so it seems like we do have a question.
A question online. Wouldn't the 2D spectra, say 2D FFT, also tend to discriminate towards sheared and simply rotated galaxy structure? Rotation would tend to suppress higher spatial frequencies, while shear would not.
Sorry, I didn't get the question.
Okay, so the question was, wouldn't the 2D spectra also tend to discriminate between sheared and simply rotated galaxy structure?
Okay. Let me think. I haven't looked into the features in Fourier space for rotation and shear, but I think that would be a good point to see how the if we can distinct the features due to shear and due to rotation in Fourier space, and I think that would be very helpful to mitigate some small scale substructures. I don't know if I answered the question.
Yeah, well, maybe continue the conversation over some. Okay, well, let's thank Doshan again. All right, so our next talk will be from Masaya Yamamoto, and he will talk to us about DES.
Hi everyone, I'm Masaya Yamamoto. I'm a postdoc at Princeton University. I'm a member of Dark Energy Survey Collaboration, and I am heavily involved in DES's year 6 final year analysis using 6 years worth of data. And I'm going to show some results from it. And of course, it is a huge collaboration, and I'm presenting results on behalf of everyone who's involved in it. Okay, I'd like to start with a flowchart of modern cosmological analysis pipeline, going from images all the way to cosmology. As you've heard in previous talks, measuring, distant galaxies with gravitational lensing signal due to cosmic structure requires knowing about galaxy shapes and their redshift distributions. Their measurements are then calibrated using image simulations, and these are used to compute the 2-point correlation. Hello? Okay. And on the theory modeling side, we make a lot of decisions on how to model the theoretical 2-point function. The components of the models include how to model matter path spectrum, especially nonlinear scale, and how to model intrinsic alignment. And at each part of the steps, there are a few challenges for making the stage 4 experiments like Rubin, weak lens experiments successful. For the data side, main challenges are whether we can construct a well-calibrated shape catalog and photometric redshift distributions from the wide field image data, and our ability to characterize the systematics that exist in the data using simulations. And on the theory side, our understanding of how baryonic feedback impacts matter clustering and how intrinsic alignment signal contaminates the actual shear signal isn't there yet. And so we currently have to sacrifice our data and precision not to bias the cosmology. In DES year 6 analysis, I am serving as a co-lead for constructing and calibrating the shape catalog, which is highlighted as green boxes. And I am also co-leading another analysis team for bringing the data together to produce the cosmological results from the data, which is highlighted as red boxes. And I will focus on both aspects of these in this talk. Okay, so let me start with the illustrating challenges associated with measuring the shear signal. I think Jirchuan covered most of it. So this illustrates how the lights from distant galaxies go through, cosmic structure, atmosphere, telescope, and detectors. But in reality, what we see is this, last thing, which is pixelated, blurry, and noisy. And so we have to process the images in order to extract the distorted galaxy shapes, which we call shear. The steps include, coding images to enhance signature noise of the objects and recover or resample pixels. Where there are challenges like aliasing, especially for undersampled images like Rubin, and PSF discontinuity arise, especially for survey like LSST. Another step includes modeling of the PSF, where there are challenges like you need to have a pure sample of input sample to model the PSF. You need to model optics, you need to model atmosphere, and including the chromaticity in the PSF is also very important. And lastly, one can measure galaxy shapes to be correlated with. However, biases arise due to some measurement algorithms, noise, selection of objects. And all these biases are basically summarized as multiplicative and additive biases in the measured galaxy shapes compared to intrinsic galaxy shapes. And to get reoriented, 1% level of multiplicative bias is about 1.5% in SA, for example. And the goal of weak lensing data from a survey is to reduce this MNC as much as possible and characterize them in the simulation so that we could marginalize them over in the cosmological analysis. So with that, I'm going to focus on the dark energy survey specific implementation of the methods and the results. So quickly, DS takes images from dark energy camera mounted on the 4-meter Blanco telescope on CTI in Chile and covers about 5,000 square degrees in the southern sky. And this footprint will have many overlaps with new surveys like Rubin and LSST and Euclid. And I have led our weak lensing data calibration team, which consists of many of our early career scientists shown here. So our image processing methods to obtain shear in Y6 have been upgraded in almost every part of the pipeline with the stage 4 challenges that I just described in mind. So these include new PSF modeling, new ways to call out images and calibrate raw galaxy shapes. And this plot summarizes our ability in DS to reduce shear biases over 10 years since the science verification stage, so going from SV, year 1, year 3, and now year 6. And demonstrates that we are achieving the level of bias required for LSST year 1, for example. And I will now go into the details of the method now. Okay, sorry. There's also image of number density going from science verification to year 6. So in terms of PSF modeling, open problems in Y3 were we had a possible galaxy contamination in the stellar samples. In the sample we used to model the PSF. And there were significant PSF modeling errors, especially in G-band. Because until now, so PSFs are wavelength dependent, but we never modeled that part. And so there were significant PSF modeling errors, especially in G-band. And as a result, we were not able to use any of the G-band information for weak lensing in DSY3. And now in Y6, we now use near-infrared surveys to select pure sample of stars to model PSF, and also use color of the input stars to model the wavelength dependence of the PSF. And as a result, the color-dependent trends improved by 80 to 95% across all GRIZ bands. And we can use all 4 bands for photometric redshifts. And it was shown to reduce, using all 4 bands was shown to reduce the biases on the photo Z distributions. And the second improvement is the way we calibrate galaxy, measure galaxy shapes. In year 3, we saw a few percent level multiplicator bias with the method widely known as meta-calibration. It is an algorithm which can be directly applied on the data and self-calibrates the raw galaxy shapes. But people realized that the detection of objects itself depends on shear. And this bias was particularly strong in blended systems. And so we started seeing, as the survey gets deeper, and we saw in Y3. And there was an update to the method called meta detection, which was tested in elasticity simulations and was demonstrated to achieve the requirements the LSSD shear analysis requires. So applying this new method to DES Y6 data was like a proof of concept. So newly estimated from our newly renovated image simulations multiband image sims, our Y6 chip catalog contains an overall of sub% level bias, which is an order of magnitude improvement compared to Y3. And tomographically, our redshift-dependent multiplicator bias is better in terms of the mean, as you can see in the plot here. And we are also achieving the level of systematic uncertainty required for LSST1. So that was multiplicator bias. In terms of additive bias, we saw a small additive bias likely caused by residual PSF modeling errors. But we have demonstrated that in the plot in the right, that this small additive bias does not cause bias in cosmology in the end. OK, so in the last few minutes, I would like to change the gear and talk about Y6 cosmic shear cosmology with the weak lensing data correlate to produce. So with all the improvements to the data just described, we obtained 150 million galaxy shapes. I think this is the most among any of the shear catalog that exists in the world. And our measurement of 2-point correlation function has the singleton noise of 40 with scale cuts. That is our modeling choice. And the plot shows the forecast of Y6 cosmic shear, so not the real data. And we expect our precision on SA to be about 2%. And we are in the stage of trying to unblind the results, so stay tuned for that. I also want to show what limits us from achieving a better precision in Y6. So the red curve contour was the same as before. But the blue curve here is the forecast, but with all the observation systematics parameters set to 0. So it is showcasing as if our data is perfect. We don't have to model any of the observation systematics. And what this shows is that our limit in systematics is not the ability to calibrate shear or photo Z. So what really prevents us from achieving a better precision? What limits us is the lack of better understanding of astrophysical modeling, as you probably guessed. So singleton noise on the cosmic shear would have been 65 if we don't have to waste any data. And if we had a perfect knowledge of how baryonic feedback impacts the matter clustering and how intrinsic alignment contaminates a shear signal, then and if we don't have to waste any data, our precision would improve by 50%, as you can see as a green contour here. So I believe that bringing the community together to better model, astrophysics is pressing for stage 4 surveys. And to conclude, the SY6 shear catalog was a proof of concept for the new shear calibration method that will be used for LSST. and is planned to be used for Roman highlight to wide area survey. And we have demonstrated that it can be applied to the real data and achieves good precision. And our weak lens in data is not the limit in systematics in our cosmological analysis. But we need to work together towards understanding the astrophysical systematics more for Roman or other stage 4 surveys to unlock the full potential of the survey. So thank you.
Well, I have a question. Think about it, and or type their questions in the chat. So maybe going forward for Roman, since you have all this experience running Metacom on DES, what do you think might be the biggest difference in trying to run the same kind of code on Roman or algorithms on Roman? Which you've already done a little bit of that, but just on maybe the real data.
I see. I guess building a well sample quality measures is very important, of course, and modeling the PSF chromatically is going to be a challenge and an important aspect. Yeah, trying to think out any other thing. Yeah.
Okay. Yeah, thanks.
Yeah, you mentioned PSF. So, because in the Metacal MetaDetect results, you sort of those are results for perfect PSF modeling, right? So, I'm just curious if you take total M budget. So, what fraction is the PSF modeling uncertainties? So, how do they compare to total error budget?
For Roman or?
Not for DES.
For DES. Yeah, so in our image simulation analysis, we have identified that whether overall M was reduced by using meta detection to avoid blending and stuff, but the rest of the majority of the remaining systematics here, M, is actually from chromatic effects. The fact that we're not using the perfect color dependence, we're not modeling the PSF fully in wavelength dependent way.
But also you have seeing variation, so even each image you will have.
Yeah.
But that's something like that.
We haven't actually tested it, every single PSF variation stuff, but the most of M we estimated that it's coming from chromatic effects.
Okay, yeah.
The color dependence of the M bias seems non-monotonic. Why is that? Middle 50% below reddest and bluest 25%.
Is that the PSF or? The question is, why is it not monotonic?
Yeah, why?
Why does it
Tapi
seem non-monotonic? Non-monotonic.
Oh, in color. I see. So we have,
in the list. You know apa? Putih.
Actually don't know.
Just because it's a second order bit, so you can think of it like a parabola.
But this is the PSF modeling error, so the galaxy color doesn't matter. If we overestimate, one side of the how do we explain?
Just to Slack. That
Yeah,
was easier. Yeah.
let's go to Slack. Sorry.
Let's do that. Thanks, Melissa. So can I have, so we just have one final session. It's the poster pops for the end of today. Could I have the speakers line up over there? We have collated, or actually thanks to Javi, Javi has collated all of the poster pops back to back. So hopefully the transitions will go a bit faster. And then each of the speakers can come up and use these mics. So first off, we have Rakshita Thaman from NYU.
Hi everyone, I'm Rakshita Thaman. I'm a graduate student at NYU. I'm presenting a poster on modeling nonlinear clustering in the cross correlations of Roman with line intensity mapping. So line intensity mapping is an emerging technique that maps the total intensity of light emission across the sky. And from these cross correlations, we will be able to learn about cosmology as well as galaxy formation and evolution during the era of peak star formation. So we create forecasts for the cross-power spectrum using semi-analytic models, which are computationally efficient and physically motivated. In particular, we use a 2-degree square light cone generated using Santa Cruz SAM. So we have some interesting results that show that Roman's wide and deep observations might enable probing the nonlinear clustering. So come by my poster. It's number 3 in the auditorium. And yeah, it's also on Slack. So yeah, thank you.
All right, so next we have Inte. And so, yeah.
Hello, I'm Inte Zhang, a postdoc here at STSCI. My poster presents my ongoing project on Roman perspective on identification of protoclusters during the epoch of reionization. So the Lyman alpha emitter searches probe reionization. Oh, yeah, yeah. The Lyman alpha emitters have been probing the reionization topology as the Lyman alpha only visible through the ionized regions during the epoch of reionization. And what's more interesting is the strong Lyman alpha emitters are uniformly found in galaxy overdensities. What that means is those ionized regions may overlap, preferentially overlap with galaxy overdensity or protoclusters. So the Roman's capability with a large field of view will revolutionize this effort, finding the numerous protocluster candidates during the epoch of reionization. So to test Roman's potential, we use a state-of-art a large volume cosmological simulation. Yeah, yeah, simulation to trace back the protocluster evolution and make mock Roman photometric catalog under the condition of a higher latitude survey. And our perspective suggests, the higher latitude survey is really promising to discover the protocluster candidate even during the epoch of reionization. So to find out more details, to check out my e-poster, or just feel free to find me during the coffee break. Thank you.
All right, so next we have Farhan.
Hi, I'm Farhan Hassan, also postdoc at Space Telescope. My poster is basically making predictions for the cosmic web structure as can be identified by wide surveys on Roman. And so basically, we've developed a model that mimics the growth of the slime mold organism that you can find here on Earth in order to reconstruct the cosmic web filamentary structure from galaxy surveys. We've applied this to the illustrious TNG cosmological simulations. And basically what we found is that even with the deepest GRISM spectroscopy that's planned on the highlighted wide area survey, which would give you spectroscopic redshifts, you would get a sort of biased sample of tracers, so you wouldn't be able to reconstruct the cosmic web faithfully and accurately. You'd actually need a survey that's at least 2.5 times deeper in order to accurately identify the Redshift 1 cosmic web. I'm poster number 4 right over there. Come talk to me. Thanks.
Is this an online one, perhaps? Okay. I guess if it is, maybe we can sort it out at the end. And for now, we will just go to Greco. Yeah.
Hello, my name is Greco Yarsun. I am a postdoc at Johns Hopkins, and my poster is about searching for signatures of assembly bias in SDSS, where assembly bias here is the correspondence between galaxy and halo properties at fixed halo mass. So what exactly did we do? So on the left, you see the stellar to halo mass relation for passive central galaxies in SDSS. And what we did was to define 2 galaxy subsamples according to their stellar to halo mass ratios. So high mass galaxies are shown in pink, and low mass galaxies are shown in green. And what we did was to study their large scale densities, which is what's plotted in the middle figure. And what we found was that more massive galaxies tend to systematically reside in higher density regions of the large scale structure, which in lambda CDM, if you use dark matter only simulations, corresponds to older halo formation times, which is what's plotted on the right. So if you're interested in learning more about this or chat about how Roman can take these types of studies to the next level, please reach out and check out my poster. Thank you.
All right, so next we'll have Sachi.
Thank you. Hello, everyone. My name is Sachi Veerasurya. I'm a postdoc at Carnegie Observatories, and I work on modeling emission line galaxies with Galactica semianalytic model as part of Open Universe effort. So as everyone is talking about, Roman is going to bombard us with many observations, right? And statistical power of semianalytic models is going to be very handy in making predictions and maximizing the impact of Roman. So what we are trying to do here is model emission line galaxies, specifically in Galactica semianalytic model, to predict the luminosities of emission lines in star-forming regions and active galactic nuclei, specifically narrow line regions. So here you can see we are able to reproduce the luminosity functions of H alpha for a couple of different redshifts reasonably well. And here you can see the observations in gray and models in blue and green. So it still needs calibration, not perfect, but we are getting there. So, and we also have comparisons to BPT diagrams, emission line ratios, and it's not too bad, still need calibration. So if you're interested in any of this, please come talk to me. And I'm also interested in scientific illustrations, so please come talk to me if you want. Thank you.
All right, so next we have Isaac.
Thanks. So this is a poster that investigates the potential of a Roman Grism deep field to constrain the number density evolution of Lyman alpha emitters at redshifts greater than 7 and place meaningful constraints on the timing of reionization. So this work involves simulating realistic extragalactic foreground scenes with observations from cosmos, and then putting in fake Lyman alpha emitters and testing our ability to recover them. So this is recovery fraction shown here, and the main takeaway here is that a Roman Grism deep field can relatively easily achieve the required survey volume and sensitivity to place meaningful constraints on the timing of reionization. And what I'd like to emphasize here is that since this publication last year, we've continued to develop higher fidelity Grism simulations, and so those are shown on the right. So this is showing second and third generation simulations, and these third generation simulations are still under development, but what we are doing here is modeling not only the 0, 0, the 1, 1, and the 2, 2, but we're also modeling these off-order, all the major off-order for the spectra. We are basing this on Cosmos Web, so we have a very wide field of view, and we are modeling the wavelength dependence of the PSF within these simulations. Thanks.
All right, so next we have Calvin.
Thank you very much. Hi, my name's Calvin. I'm a third-year PhD from Cambridge, supervised by Alex Amon and George Sathu. You can find my poster to the stage right over there at stage number 10, and it's titled Cosmic Shear as a Probe of the Nonlinear Universe. So no one cosmological probe is unique, and that's summarized in this plot here. It's a function of scale, large scale to small scales on the x-axis, and a function of redshift on the y-axis. So high redshift linear probes like the CMB exist in the top left, and weak lensing is down on the right. And this sort of ominous color scheme really represents how hard it is to handle the systematics. That's not to say that CMB is easy and weak lensing is hard. It's really to say that CMB is hard and weak lensing is really hard. So on the far right there's lots of scales that we can learn about, but what my poster really looks at is how we can extract the most from the full range of cosmic shear weak lensing data. So if you want to learn more about that and clever ways of extracting that data, come see my poster over there. Thank you very much.
All right, so I think we saw Majideen online, but doesn't seem to be in the room. I don't know if you heard anything else. Okay, well, I will keep this up here for a little bit, and then you should check out the poster. So just a few more announcements. Yeah, that pretty much concludes today. So tomorrow we'll be back for session 10, which is mini workshops. So please do come to hear about preparation for cycle 1 proposals. Also, yeah, including things like the Roman Research Nexus, which some people had alluded to yesterday and today, and also presentations from the project infrastructure teams and kind of just generally what they're about and how you might get involved. Okay, so after that, I think we have a couple of open polls, one for questions that you want answered by the survey panel on Thursday, and also just general science interests. So please do fill those out. But aside from that, let's thank the speakers one more time and the poster prep. All right, thanks. Have a good dinner.
Are you going out tonight?
For